Hey guys, welcome to our long anticipated unit on trigonometry. As you may know, fourth quarter Algebra 2 Honors is all about this idea of trig. And listen, trig is something we're going to need to know once we advance beyond this class. You're going to need to know trig for pre-calculus, you're going to need to know it for calculus, and if you move on to a mathematical related field in college, you are certainly going to be utilizing this idea of trig. So we're going to spend some time in this class introducing you to trig, and we are going to make sure that you leave this class feeling confident once you step into those future math classes. So we are going to begin our study of trigonometry with trig number 1 on angles and their measures. Now, before we jump into trigonometry, I do want to give you some brief context, and I want to talk about the historical applications of trigonometry and how trigonometry was developed. So, engineers in the ancient world discovered ratios within right triangles as they learned fundamental engineering skills. The secrets and patterns necessary to understanding circles and spheres helped in the development of trigonometry. Now, our unit on trigonometry is going to start with a brief introduction into angles and their measures. All right, let's go ahead and start by defining vocabulary that deals with angle characteristics. Now, in trigonometry, an angle is determined by rotating a ray about its endpoint. And before I start defining vocabulary words, let's go ahead and talk about what this means by looking at the visual that we have over here to the side. So ignore the vocabulary words for now. All I want you to look at is I just want you to look at this ray that I have drawn right here. So if I were to have some ray and I wanted to rotate that ray counterclockwise some number of degrees, and let's say this is the rotated version of the ray right here, this rotation of that ray is going to create an angle, which I'm going to call theta. And here's a couple of vocabulary words that we will use to describe the angle that is created by this rotation. So the vertex, that is the endpoint of the ray. So the ray that we started with is right here. The endpoint of that ray is the vertex. We also have the initial side of an angle. And the initial side is the starting position of the ray. So since my ray started right here before I rotated it, this is referred to as the initial side of the angle. Now the terminal side, that is the rotated version of the ray. So the terminal side is the position after rotation, which is this side right here that I found when I rotated my ray. And as you know, the initial side and the terminal side of the angle is going to form some angle between the rays, and I'm going to call that theta. So this is how we deal with angles when we are looking at trigonometry. Okay, so now that we understand how angles work in the unit of trigonometry, let's talk about a couple more characteristics that we're going to notice about these angles. And the first thing I want to talk about is standard position angles. Angles that are in standard position are placed on a coordinate plane with the vertex at the origin and the initial side on the positive x-axis. So if you take a look at the visual over here, the vertex of the angle, that is smack dab in the middle of the graph at the origin. And like we said, the initial side is on the positive x-axis. So this is going to be the starting ray for all of the angles we deal with in trigonometry for this class, all right? Now, there's two different directions we could go from the initial side of the angle. We could either go counterclockwise, and if we go counterclockwise, that's going to create a positive angle measure. Okay, so positive angle measures are determined by counterclockwise rotations. Or from the initial side, we could go clockwise. Now, if we have a clockwise rotation, that's going to give us a negative angle measure. Okay, so negative angles are determined by clockwise rotations. So just keep this in mind, the direction that you rotate your ray is going to influence the sign of your angle measure. Okay, so on the topic of standard position angles, we also have the topic of coterminal angles. So two angles in standard position that have the same terminal side are called coterminal angles. We can find an angle that is coterminal to a given angle simply by adding or subtracting one revolution. And let me kind of explain to you what this looks like visually. So let's say I have some angle in standard position. We know that the initial side has to be the positive x-axis. And let's say the terminal side is somewhere right here in the third quadrant. Well, if I take a look at my terminal side, let's say that I make a full counterclockwise rotation around the coordinate plane, and I end up right back here at my terminal side. What I have just done is I have created a coterminal angle. And think about it, since I moved counterclockwise in a full circle, I have essentially added 360 degrees because we know that counterclockwise rotations are positive angle measures. So the original angle measure plus 360 degrees creates a coterminal angle. The terminal side is still the same. And the same works in the reverse as well. So if I start at my terminal side and I make a full clockwise rotation, clockwise rotations create negative angle measures. And since I made a full circle, I essentially subtracted 360 degrees. And since the terminal side is the same, I have created a coterminal angle when I subtracted 360 degrees. And this is how coterminal angles work. You just add or subtract 360 degrees. Now with this in mind, any angle, any given angle, has many coterminal angles. And think about it. We can make tons of rotations around the circle. All we have to do is we just have to add or subtract 360 degrees each time. So there are essentially infinite numbers of coterminal angles for any given angle, all right? Let's look, for example, at beta equals 36 degrees. Well, some examples of coterminal angles for this angle measure 36 degrees are some of the following. 396 is an example of a coterminal angle. All I did was I added 360 degrees. 756 is also a coterminal angle because all I did is I added 360 degrees 2 times. So I made 2 counterclockwise rotations. Another example might be negative 324. Maybe I subtract 360 degrees. We also have negative 684. I subtract 360 degrees 2 times. Okay? Or in other words, I make 2 revolutions in the clockwise direction. So all of these are examples of coterminal angles for 36 degrees. Now, with this in mind, let's look at example number 1. We need to draw theta equals 220 degrees, and we need to label theta prime as an angle that is coterminal. Well, the angle that I drew over here just so happens to be the sketch of theta equals 220 degrees. And what I have done is I have moved from the initial side to the terminal side in a counterclockwise rotation. And think about it. So if I make a rotation 90 degrees, that's going to be right here, this right angle formed with the x and y axes. All right, a rotation to the other side of the x-axis, that's a 180 degree rotation. And so a little bit greater than 180 degrees is 220. So that's kind of how we visualize what 220 degrees looks like. Now, a coterminal angle, the easiest one to find is going to be this one right here. So from the initial side to the terminal side in a clockwise rotation. And the way that we can find this angle measure is all we have to do is take 220 and subtract 360. And that's going to give me negative 140, right? And so we know that negative 140 is going to be this coterminal angle, theta prime, negative 140. And that makes sense because if we were to rotate from the x-axis to the negative y-axis, that would be negative 90 degrees, all right? And then if we have to get the rest of the way over here, that's going to be negative 140 degrees. Okay, so obviously that's a coterminal angle. Now another example of a coterminal angle, well, theta prime could also be 580 degrees, right? Because we know if we took 220 and we added 360 to it, that would also give us a coterminal angle, and that would give me 580. So that's another example. There's obviously infinite numbers of examples though, so let's go ahead and describe what those examples would look like. So it could be 580 degrees, or really any full rotation, or I'm going to say any full revolution of 220 degrees plus or minus 360 degrees times some variable n, where n is any integer. Okay, so what this is saying is that I could take the original degree measure, 220, and I could add or subtract some multiple of 360, and that's going to give me all the possible coterminal angles for 220 degrees. All right, so on to the next page. We have one more vocab word before we start to get into some examples for today. So reference angles. Given an angle in standard position, its reference angle is the acute angle that is formed by the terminal side of the given angle and the x-axis. So if we take a look at the example over here to the right, it is given that this angle is 210 degrees. And that makes sense because if we go from the initial side and we make a quarter circle, well, a quarter circle is 90 degrees. Then if we made a half circle, that's 180 degrees, right? And then a little bit below 180, we will come to 210. So that is why 210 degrees looks like this drawing right here. Now, again, the reference angle is the acute angle that is formed by the terminal side and the x-axis. So the terminal side of this angle is right here, and the x-axis is right here. This tiny little acute angle is the reference angle. Now, how do we find the measure for the reference angle? Well, in order to find the measure, we're going to have to look at the angles around it that we already know. Like I said previously, if we make a half circle, that measure is 180 degrees. So if I know that this chunk of the angle is 180, in order to find the missing chunk down here, I'm just going to take 210, the total angle measure, and subtract what I know, 180. So 210 degrees minus 180 degrees, that's going to give me 30 degrees. So what this tells me is that this tiny little chunk is 30 degrees, so the reference angle is 30 degrees. Let's do some more practice. So example number 2, draw each angle and state the reference angle. We're going to start with 150 degrees. In order to draw any angle, I always find it useful to know the landmark angles around it, just so that you know kind of where your angle measure is going to fall in relation to the angle measures that we already know. So just keep in mind, from the initial side, if we made a quarter rotation, that would be 90 degrees, and that makes sense because it forms a 90-degree angle or a right angle. If we made a half circle rotation, that would be 180 degrees. If we make 3/4 of a rotation, that's 270 degrees. And obviously a full rotation around the circle will be 360 degrees. So if I'm going to draw 150, I need to think to myself, which one of these landmark angles is 150 closest to? Well, I know that 150 is kind of close to 180, and 180 is that half rotation around the circle. So 150 is going to have to be a little bit less than that half rotation. So I'm going to say that 150 degrees is this angle measure right here. Now to find the reference angle is just going to be the acute angle formed by the terminal side and the x-axis. Now if I know that this angle measure is 150, the full angle measure is 180, in order to find that missing chunk right there, well, what do I have to add to 150 to get to that full 180? And the answer is 30 degrees, all right? So the reference angle is 30 degrees because 150 plus 30 will give me that half rotation of 180. All right, 2B, we have 315 degrees. So think to yourself, what is 315 degrees closest to when I'm looking at my landmark angles? Well, 315 is obviously more than 270, so it's going to be more than 3/4 of a rotation, and it kind of falls smack dab in between 360 and 270. So I'm going to say right here, this is 315 degrees. All right, so from the initial side, I made that rotation, 315 degrees, and that is my angle measure. Now to find the reference angle, I need to find, okay, well, from this angle, 315 degrees, the rest of the way to 360 degrees, what do I have to fill in, okay? What is this missing chunk here? Well, an easy way I could find this is I could take the full rotation, 360 degrees, and I could just subtract 315 degrees, and that will give me the missing chunk that will fill in the full circle. And if I take 360 minus 315, that gives me 45. Oops. There we go, 45 degrees. So that means my reference angle is 45 degrees. And I'm just gonna say ref angle. All right. Next up, we have negative 120 degrees. Just keep in mind with negative angle measures, we are going in a clockwise rotation from the initial side. So If I'm going clockwise, it's the same exact thing. This will bring me to negative 90, a quarter rotation. A half rotation will give me negative 180. 3/4 of a rotation will give me negative 270. And then obviously a full clockwise rotation will be negative 360. So negative 120, that's going to be a little bit more than negative 90. So I'm going to say negative 120 is right about here. Okay, it's just slightly farther to the left there than negative 90 is. So from the initial side to the terminal side, that is negative 120 degrees. And the reference angle is just going to be the acute angle that is formed by the terminal side and the x-axis. So this is the reference angle right here. I need to find what that is equal to. So the way I could do this is I could say, all right, well, if I know that a half rotation would be negative 180, what do I have to do to get from negative 120 to negative 180, all right? What is this missing chunk going to be? Well, if I subtracted 60 degrees from negative 120, that would bring me to negative 180. So my reference angle is going to be 60 degrees, okay? And we're going to write the reference angles in terms of positive numbers, okay? So that's just going to be positive 60 degrees from the terminal side to the x-axis. All right, and then 2D, we have 140 degrees. So once again, 140 is kind of like in the middle between 90 degrees and 180 degrees. So I'm gonna say 140 is right about here. Okay, so if 140 is right about there, from the initial side to the terminal side, that's 140. The reference angle is gonna be this angle between the terminal side and the x-axis. All right, and again, I'm thinking to myself, well, how do I get from 140 to the landmark angle 180? Well, I would just have to add 40 to it, okay? Because if I added 40, that would bring me to the half circle, 180. So my reference angle is 40 degrees. Again, and that's my reference angle. All right, let's go ahead and move on. So up to this point, we have only talked about whole number degree measures. Now I'm going to introduce the idea of decimal degree measures to you. And when we are talking about degree measures that have decimals, there is a different unit that we are going to be using. And this unit is degrees, minutes, seconds. So in other words, we can write decimal degrees in terms of smaller units called minutes and seconds. And in order to do so, here are some conversion factors that we're going to have to be aware of. So there are 360 degrees in one revolution around the coordinate plane. We already know this, but what we don't know is what minutes and seconds are represented by. So 1 degree is equivalent to 60 minutes, and furthermore, 1 minute is equal to 60 seconds, just kind of like the actual clock is, right? And if I wanted to jump from degrees to seconds, well, since there is 60 minutes in 1 degree, and every minute has 60 seconds, 60 times 60 gives you 3,600. So 1 degree is equivalent to 3,600 seconds. And we're gonna use these conversion factors to convert the following. So for 3A, we need to convert 36 degrees, 25 minutes, 18 seconds into decimal degrees. So instead of using this unit, degrees, minutes, seconds, I want to convert this to a regular decimal. So here's what we're going to do. We are going to treat the degrees as if it was the whole number component of the decimal, because it is. So I'm going to leave 36 degrees alone. I'm just going to write that out front. So 36 degrees stays the same because that's the whole number component. But what I need to do is I need to convert minutes and seconds into decimal degrees. Well, if I know that 1 degree is 60 minutes, 25 minutes can be represented as 25 over 60. And that's going to convert my minutes into decimal degrees because, again, there is 60 minutes for 1 degree, so 25 minutes is represented as 25 over 60. Now I need to convert 18 seconds. And well, what I know is that for every 1 degree, there is 3,600 seconds. So 18 seconds can be converted to degrees by taking 18 and dividing it by 3,600. So if I convert these to decimals, that will allow me to add all of these together and give one final decimal degree measure. So 25 over 60, if I write that in decimal form, that's going to be 0.41666. If I convert 18 over 3600 to a decimal, that's going to give me approximately 0.005. If I take all three of those and add them together, I'm going to get 36.4217 degrees. And that is my conversion from minutes, degrees, minutes, seconds into decimal degrees. Now, what if I wanted to do the exact opposite? So for 3b, we have convert 42.575 degrees to degrees, minutes, seconds form. Well, here's what I know. I know that 42 is my whole number component, so the first thing I'm going to have is 42 degrees in my answer. I don't have to worry about that, though, because that's super easy. But now I need to figure out, okay, well, how do I convert this decimal 0.575 to degrees, minutes, and seconds? Well, what I can do is I can use first the minutes conversion to convert this decimal into minutes, and then whatever decimal I have from that point forward, I can convert into seconds using this conversion factor. So I'm going to start with 0.575 degrees, all right? And if I multiply that by 60 minutes for every 1 degree, that's going to convert this degree measure into minutes. And the reason we're setting it up this way, we're multiplying by the number of minutes, is because now my degrees will cancel, and this is going to give me my minutes measure. So, obviously, like I said, my degree signs will cancel. 0.575 times 60, that's going to give me 34.5 minutes. Now, obviously, I don't like decimals because I'm writing this in degrees, minutes, seconds form. So this 0.5 is going to have to be converted even more down into seconds. So if I take 0.5 minutes and I want to convert that into seconds, well, there are 60 seconds for every 1 minute. And the reason I'm setting it up this way is because now my minutes will cancel, and 0.5 times 60, that's going to give me 30. So I have found that converting 42.575 degrees to degrees, minutes, seconds, well, the whole number is 42, so I have 42 degrees. The whole number for the minutes is 34, so I have 34 minutes. And then I converted that 0.5 into 30 seconds. So this is my degree measure in degrees, minutes, seconds form. So use the conversion factors, multiply some stuff, make sure you set it up in a way where the units that you want to cancel will cancel. Okay, so moving on to the next page, we are now going to discuss a different way of measuring angles. So up to this point, we have measured angles in terms of degrees, but just like feet and inches, there are other ways to measure the same thing, just using different units of measurement, right? So another way to measure angles is in radians, all right? So radians is another way to represent those angle measures. And let me give you some context about radians. So in the late 1800s, mathematicians began to see a need for another unit of measure. Now, because they needed an angle measurements to cancel out, that's why we developed this idea of radians, because they needed cancellation when they were dealing with simplifying mathematical and physical formulas and all that stuff. So that is why they developed the idea of a radian. Now, here are a few things to know about radians. First of all, radians have no units. There's nothing written after them. There's no symbol or anything like that. One complete circular revolution is 2 pi radians, okay? So one entire revolution around the circle is represented by 2 pi. And the last thing to know is that 1 radian is approximately 57.296 degrees. Now, the definition of a radian is based on the concept of a unit circle. And we're going to be talking a lot about the unit circle in this unit. And the unit circle is basically a circle that has a radius of 1 unit with its center at the origin of a coordinate system. The radian measure of an angle is based on the length of an arc on the unit circle. So, with that being said, let's go ahead and scroll down a little bit and talk more about this idea of a unit circle. So central angles on the unit circle. We use the central angle of a unit circle, shown, this is actually to the right, where the vertex is the center of the circle. 1 radian is the measure of the central angle that subtends or intersects an arc equal in length to the radius of the circle. The circumference of any circle, as you know, is 2 pi r, where r is the radius measure. So the circumference of a unit circle where r equals 1 is 2 pi times 1 units. Therefore, an angle representing 1 complete revolution of the circle measures 2 pi radians. So again, that's just kind of some of the background there that describes this idea of radian measures. We said before that 1 revolution around the circle is 2 pi radians, and that again is based on the unit circle, which has a radius of 1. So 2 pi times 1 will give us a circumference of 2 pi. So that's kind of where all of that stuff is related. Now, if theta is a central angle in a circle of radius r, and if theta is measured in radians, then the length s of the intercepted arc is given by s equals r times theta, okay? Now let's talk about some common radian measures that you will be seeing during this unit. So what we're going to do is we're going to sketch each of the radian measures on the coordinate plane below. But first, let's draw some characteristics about radian measures in relation to where they lie on the coordinate plane. So if I know that a full rotation around a circle is 2 pi radians, then a half rotation around the circle will have to be 1 pi radians. Furthermore, a quarter of a rotation will have to be pi over 2 radians. And if we continue this trend where each quarter circle is pi over 2, that means that this 3/4 rotation is going to be 3 pi over 2. So using this information, let's go ahead and sketch negative pi over 4 radians. Well, same rules apply if we have a negative degree measure, or in this case, a negative radian measure. We are going to be going clockwise from the initial side. So pi over 4 is going to be halfway in between 1 pi over 2 rotation, which is a quarter of a circle. So essentially, we are making an eighth of a rotation in the clockwise direction. So negative pi over 4 is going to be smack dab in between the starting initial point and 3 pi over 2. And again, this is going to be negative pi over 4. All right, now let's go to pi over 2. Well, like we said, pi over 2 represents every quarter rotation around this circle. So pi over 2 is just a quarter rotation from the initial side to the y-axis. So this is pi over 2, all right? Just recognize that pi over 2 represents that right angle, okay? And that's going to be a common characteristic that you need to use throughout this unit. And then pi radians, well, like we said before, pi is going to be a half rotation around the circle. So from the initial side to the terminal side, this is what pi radians will look like. All right, you guys, so on to the last page of the notes for today. Now, just a quick warning, I was kicked out of the school building just because I was staying way too late. So I did have to transition home for the last section of the notes today. And if you guys are in my classes, you know that my dog is a psychopath. So he's currently running around with his new toy, like running into things, knocking things over, like crashing things. It's just, I apologize if that becomes a distraction, but we're just going to make do with what we've got and we'll do the best we can. So now we're going to talk about converting between units of angle measure. Now, just like we can convert from meters to feet or inches to centimeters, same thing with angle measure, right? We can convert from degrees to radians and radians to degrees pretty easily. The only thing we're going to do is we're just going to multiply by a conversion factor. So to convert degrees to radians, here's what we're going to do. So from degrees to radians, we are going to multiply the degrees by pi over 180. Now, why are we multiplying by pi over 180? Well, think about it. Pi and 180 are the same exact angle measure, right? They are both equivalent to 180 degrees. So essentially, this is like multiplying something by 1. Now, the reason we set it up this way so that 180 degrees is in the denominator is because whatever the degree measure is that I'm trying to convert, that degree symbol will cancel with the degrees in the denominator, and I'll just be left in terms of pi. And that's exactly what I want if I'm writing my angle measure in radians. Now, to do the opposite, we're literally just going to multiply by the reciprocal. So from radians to degrees, we're going to multiply by 180 over pi. And once again, this is just like multiplying by 1 because 180 and pi are the same measure. And this time, the pi of my original is going to cancel with the pi in my denominator. And then I'm just going to be left in terms of degrees, which is exactly what I want if I am converting to degrees. With that being said, let's go ahead and move to example number 4, and we are going to convert each angle from radians to degrees or vice versa. Now for A, B, and C, all three of these are represented in terms of pi, which tells us that these are radians and we are going to convert them to degrees. So we will be using the second scale factor, 180 over pi. So let's take 7 pi over 6, and we're going to multiply by 180 over pi, and that's going to cancel out our pi's, which is exactly what we want to do. Now, from this point forward, all I got to do is simplify, because obviously I want this degree measure to be in simplest form. So 6 goes into 180 30 times, and I know that 7 times 30 gives me 210, so my angle measure is 210 degrees. All right, for the next one, once again, we are converting radians to degrees, so I'm going to multiply by 180 over pi. So let's go ahead and see what we get. All right, well, I know first of all, my pi's are going to cancel. And I know that 3 goes into 180 a total of 60 times. And negative 2 times 60 is equal to negative 120 degrees. So negative 2 pi over 3 is equivalent to negative 120 degrees. Last but not least, negative 8 pi over 15. Once again, we multiply by 180 degrees over pi. First thing that cancels is my pi symbol. All right, and now let's see what else can simplify. Well, I know that 15 is going to go into 180 12 times, and then negative 8 times 12, that's going to give me negative 96, and we do have the unit degrees. All right, so how do we do the opposite? Now I want to convert from degrees to radians. Well, now we're going to multiply by the reciprocal of what we multiplied before. I'm going to take everything and multiply it by pi over 180. And that's exactly what we want to do, because then our degree symbols will cancel. So for my first example, degree symbols cancel first. Now, obviously, all I have to do is simplify. Well, this isn't going to simplify very cleanly, so let's see what we got here. Well, 135 and 180, at the very least, I know both of those are divisible by 5. So let me take 135 divided by 5. That's going to give me 27. And then 180 divided by 5, that's going to give me 36. And I know that 36 and 27 are both divisible by 9, so I could break it down even farther. 27 divided by 9 is 3. 36 divided by 9 is 4. So I'm going to be left with 3 pi on the top and 4 on the bottom. So the radian measure of 135 degrees is 3 pi over 4. Same thing for 320. Let's multiply that by pi over 180, see what we get. Well, for this one, it's a little bit easier because we can easily see that both of these are divisible by 10. All I have to do is just get rid of the 0 and then get rid of that degree symbol, okay? Now I'm just looking at 32 and 18. I know that 32 and 18 are both divisible by 2. 32 divided by 2 gives me 16, and 18 divided by 2 gives me 9. So my final answer, since that can't simplify anymore, is negative 16 pi over 9. Last but not least, let's look at negative 110. Once again, I'm going to multiply by pi over 180. And again, both of these are divisible by 10, so I can just cancel out the 0 and the degree symbol. And 11 and 18, those don't simplify any farther. So my final answer is negative 11 pi over 18. And that is how you convert from degrees to radians and vice versa. Now let's go ahead and scroll down a little bit, and we're going to discuss more about radians. So for the first example, for practice with radians, how many radians is in each angle of an equilateral triangle? Well, an equilateral triangle is a triangle that has equivalent angle measures for all three of the angles. And we know that a triangle measures up to 180 degrees if I add all of my angles together. So 180 divided by 3 equal parts is going to be 60 degrees. And 60 degrees can easily be converted to radians by multiplying pi over 180. And I know that 60 goes into 180 a total of 3 times. My degree symbols cancel. So the radian measure for an equilateral triangle is going to be pi over 3. All right, number 2, the minute hand of a clock travels how many radians in 15 minutes? Let's go ahead and draw a visual here. If I've got a clock, I know that if my minute hand starts up here and I travel 15 minutes, that's going to be a quarter of my clock right there. And we know that a full circle is 2 pi radians, so a quarter of a circle is going to be 2 pi divided by 4, which is pi over 2. So 15 minutes is pi over 2 radians. Now, number 3 is a little bit different. The minute hand of a clock travels how many radians in 10 minutes? Let's go ahead and think about this. So once again, if I were to draw a clock here, let's go ahead and draw 15 minutes again, just so I can draw a little distinction here. So if 15 minutes is a quarter of the circle, let's go ahead and break that off into 5. So 5 minutes is going to look something like this. 10 minutes is going to look something like this. So 10 minutes is going to be 2/3 of the radian measure of 15 minutes. So what I can do is I could just take 2/3 times pi over 2, all right? And the 2's are going to cancel. And I'm just left with pi over 3. So 10 minutes is going to be represented by pi over 3 radians. Same thing with the 5 minutes. We're just going to do 1/3 instead. So if I have my clock right here and I have 15 minutes, I know 15 minutes is a quarter of the circle, and that's pi over 4 radians. So 5 minutes is going to be 1/3 of 15 minutes. So I'm going to say 1/3 times pi over 2, which was 15 minutes. And if I simplify this, I'm going to get pi over 6. So 5 minutes is pi over 6 radians. Example number 5. What is the measure of theta in radians if x equals 45 degrees? All right, well, here's the deal. I've got this kind of a situation where I've got theta all the way around the circle right here, except for this little chunk. This little chunk of my circle is 45 degrees. So what I can do is I can take the whole circle, which I know is 2 pi, and I can subtract that little segment 45 degrees. Now, 45 degrees is half of 90 degrees, so that means it's exactly halfway between the y-axis and the x-axis, and we know if we convert that to radians, that would be pi over 4. So I can take the whole measure of the circle, 2 pi, and subtract the tiny little segment right here with x, which is converted to pi over 4. Obviously, in order to subtract a fraction, I need like denominators, so I can convert 2 pi to 8 pi over 4, and I could subtract pi over 4. So theta is going to measure 7 pi over 4, and that's my final answer. Last but not least, example number 6, what is the measure of theta in radians? Well, if I have theta right here, and I have x right here, what this is telling me is this whole thing is going to form pi, right? Because a half circle is pi radians. So x plus 5x, that's going to have to equal pi radians. Oops, x plus 5x, not 5 pi. That's going to have to give me pi radians because both of these put together will form that pi rotation, right? That half circle rotation from the initial side. So if we combine like terms, I'm going to get 6x equals pi, divide both sides by 6, and I find that x is going to equal pi over 6. So x equals pi over 6. So if x equals pi over 6, that's not my answer. The question was asking what is theta equal to, and theta is represented by 5x. So I'm just going to plug in pi over 6 for x, and I find that theta is equal to 5 pi over 6. And that's my final answer. Let me clean this up a little bit because that looks a little messy. All right, guys, and that is how we deal with radians and degrees and all that good stuff. And congratulations on finishing your first trig lesson. Nice work, guys. Make sure you log in and do your homework and ask questions if you have them. And I will see you back here next time. Thank you.